So my poster is about H2CO, which is formaldehyde in the Horsehead nebula, and as an evidence of photodesorption from ice mantles. So it's known that some molecules can be formed in the gas phase in the ICM, and they can also be formed on the surface of dust grains. Okay, so formaldehyde is one of these molecules that can be formed in both scenarios. So we try to study this mechanism here in the Horsehead, which is shown in this picture. Here you have a star in this direction, so it's been illuminated in this side. And what we do is integrate, have deep integrations of formaldehyde lines towards two positions that we call the PDR and the core. The PDR is the edge of the nebula, so it's warm, and the core is a little bit, it's colder and it's shielded from the radiation. So these are the lines that we have down here. We have several lines, and what we try to do is see how much of H2CO is there in the nebula. So for this we use a Monte Carlo radiative transfer curve in which we try to model the line profiles, and that's are the colors, different colors. And once we have the column density, we use a photochemical model to study the chemistry. And this is shown here. Here you also have the star in this direction, so this is the distance, and I show the abundance here. The red lines are HCO and the blue is formaldehyde, and we use two different chemistries. One is where H2 is formed only in the gas phase. Those are the continuous lines. And we also try another chemistry in which the formaldehyde can be formed also in the surface of grains. And these are the dashed lines. So what you see basically is that in the core, that was the disposition, both models can reproduce this abundance very good. But when you go to the PDR, the gas phase chemistry is not enough. So basically what we say is that in the PDR, we need an external mechanism that is surface chemistry. And actually what is happening is that the formaldehyde forms in the grains and there gets released to the gas phase through photodesorption.
My poster is about some exciting new results from a space telescope called Herschel, and it's looking at a source in the sky called Orion KL, which is part of a well-known object that we all recognize in the night sky, the Orion constellation. And this is a really well-known source in astrophysics because it's the nearest source where there is a massive star formation going on, which is the most common form of star formation. So there are these massive stars forming within this region. And so this work is really looking at trying to understand the conditions in the gas and dust which are present in this region, so that we understand more about the environment in which star formation happens and how that affects its environment. And I'm looking at spectra taken from an instrument called HiFi on this space telescope Herschel. And this molecule that we're looking at in these spectra is an excellent temperature probe for the warm gas in this region. So what we can do is by analysing these spectra, we're able to infer the gas temperature and the conditions within this region where these massive stars are forming. And that gives us more information about how the stars form, and then also how those stars then heat their environment around them and impact generations of future stars that might form in the region. So in addition, we also have some maps of this as well, taken with a different telescope, a telescope on the ground. And these show us that the warm gas in this region is not just concentrated in the central parts where the stars may be forming, but it's also more extended throughout the region as well. So we can say something about the larger scale structure of this Orion nebula environment.
This research really focuses on the question how stars form out of molecular gas. Most of what we know about star formation has been derived from what we have observed in our own galaxies, where we see that stars always form in groups of stars, and they also form always with the same composition, that is every group has the same number of very high mass star or low mass stars. And the question is whether that is true for all galaxies, and especially for starburst galaxies like M82 and NGC 253, which are very energetic galaxies where a lot of supernovae have gone off and have pumped a lot of radiation into their environment. So we have found a method to trace the properties of the molecular gas by looking at a specific molecule and by observing the fingerprint of this molecule, different spectral lines, we can derive the temperature and density of the molecular gas in these external galaxies. And that will tell us whether star formation actually proceeds in these galaxies as it was in our Milky Way or not.